Hello and welcome back. So in this video, which is part of the series of videos for the Computational Neuroscience course taught at the University of Waterloo in winter 2021, we're going to do a live example of building up a model using the neural engineering framework. So in the last video, we sort of introduced the neural engineering framework as a sort of a method for doing something like programming with neural networks, so building up large systems out of building up full systems out of all neurons, and being able to adjust those sorts of models to be various levels of biological plausibility. But since it's such a weird way of building neural networks, I think it's really useful to show an example of building up a network using this approach. And so I'm going to go this is my standard example that I've done for when introducing people to the neural engineering framework for a while now. And what it is we're trying to build sort of the simplest little tiny bit of a brain. So I want something where we've got to deal with sensory input, we've got some sort of motor output. I want a little bit of memory that's required and a little bit of decision making required. So this is sort of, I think, at least touching on the core things that brains need to be able to do, and hopefully show an example of how we might build a system, all using exactly the techniques that I just described in the previous video of everything is just small little trained up neural networks, each of which does their own function, and then we combine them together and making use of various different synapse models to affect the calculations a little bit. The software that we're using is Nengo. It's a Python package that you can just install it with pip install Nengo. I'm also using the graphical interface, the optional graphical interface that comes with it. I gave instructions on how to install that in the previous video, or just go to nengo.ai, and there's lots of instructions there. I'll just write that, nengo.ai. That'll be the website where you can go find everything about it. But when you run it, it just appears in your web browser. And the way it's going to be structured is on the right side of the screen is just a normal text editor, and we're just going to be writing Python code. And on the left side of the screen, we're going to actually see the model and be able to run it a little bit. So what are we going to build? We've got this really, really simple critter, as I said, and here's what it's got for sensors and motor actions, and then we'll go from there. So it's just a little critter that its motor outputs are just sort of, well, what direction to move in, and we'll say that this is in a little 2D world. It can move on the x-axis, it can move on the y-axis. That's it for movement. So something pretty simple. So it can move left and right and up and down. Or some combination thereof. We're also going to have sensors. One sensor is just going to be sort of the general level of brightness. Is it bright out or is it dark out? That's a nice simple one. And then we're also going to have another sensor that's maybe something like smell, some sort of indication of what direction is food in. Okay? Or what direction is some target in. We'll call it food, whatever. And then what we want this brain to do is, well, if it's dark, then it's safe, go out into the world and go find that food. And so just go in the direction the food is in, that you're sensing that. But if it's bright out, then I want you to run back to where you started from. And that's where we're going to need a little bit of memory, because it's going to need to remember where it started from in order to do that task. Okay. And we want to build all of that out of neurons. It would be a nice simple thing to build with normal programming, but we want to build all of this out of neurons just to sort of see how we might build that sort of neural network. Since we don't have a particular biological system to compare this to, we're just going to use, just by default, we're just going to use leak, integrate, and fire neurons, and we're not even going to bother setting the parameters particularly much. I might show a little bit of playing around with that. But we're not going to be extensively focused on exactly how to map that onto the biology. We'll just use defaults for everything. But again, there's lots of documentation for how to go ahead and modify that. So how in the world are we going to do this? All right. So this will also be a little bit of introduction to the Nengo coding as well. It's a Python package, so the very first thing we're going to do is we're going to import Nengo. That'll give us access to the Nengo stuff. And then the very first thing we're going to do in Nengo is define a network. A network is just a container to put a bunch of stuff in. So it doesn't actually do anything of itself other than it's just an organizational structure. Here's where we're going to be able to put out everything into our model. We're going to do this slightly strange Python syntax of with model. What I'm just going to say, what that's going to do is that's just say, hey, everything I'm about to define now, put that inside the model that I just created. It just saves us from having to say model.add or something like that. It's just, I'm making a bunch of stuff, put it inside the model that I just created. All right. Where are we going to start building this brain? So I want to start with the simplest thing. So let's just start by defining a group of neurons that are our sensory neurons for that initial brightness. So some group of neurons that is getting input from the outside world, which is how bright it is, and it's going to be some neural activity that represents that brightness. All right. Let's say we just call this, we're going to call it light. So terminology, an ensemble is a group of neurons. We can think of it as basically like those blue circles in the video that I just showed before. It's a group of neurons, one layer of neurons. That's the other way we can just think of it. That has, and of course there's going to be some number of them. So we're going to say, I don't know, there's 100 neurons. But the other thing that happened whenever I was showing those models in the previous video was anytime I had a group of neurons, there was some number of inputs going to those neurons. And that was what gave us the encoder, that connection weights that took some number of inputs and fed it into all of those neurons. Okay, so the ensemble is sort of encapsulating that input, and so the input layer and the hidden layer would be the way to say it. So we also need to say how big that input layer is. And it's going to be one dimension because it's one thing that's being fed into this. Right. There's a lot of other parameters we can sort of specify in here as well that'll do things like control the distribution of the weights that are generated for that layer, the connection weights between the input and the hidden layer. But one big thing that might be useful is, yes, you can specify a neuron type in there. There's a whole bunch that are built into Nengo. The default is a leaky, integrate, and fire, but there's also rectified linear and sigmoid and rectified linear. That's all there. But we're going to stick with the default of leaky, integrate, and fire. Again, Nengo supports both spiking and non-spiking neurons. No problem. All right, so we have a group of neurons. You'll also notice that it sort of appeared over here. And if we take this group of neurons, now we can start doing things with this. We can right-click on it and we can say, I don't know, let's see what the spikes are coming out of this. Okay. And then we can press play. And oh, okay, cool. We have, here's a bunch of neurons. We're plotting some of them and we're seeing some spiking activity. What else can we do here? Well, we can look at the firing pattern. So it's just another view of that same data. There's all the neurons. They're just laying out. They're sitting there spiking away. So those are sorts of default graphs that will appear. But of course, that's kind of not interesting because we don't, at the moment, we don't have any way of changing the input to this group of neurons. So let's go ahead and add in something that'll let us adjust that. So we're going to, this is some stimulus for the light. Now this input isn't neurons. So anything in Nengo where we are defining something that's not neurons, we're going to call that a node. And a node, I could put a function in there to just generate data. I could put whatever function I want in there in order to generate what I want. In this case, I'm just going to say a node that just outputs 0 all the time. The reason I'm going to be able to get away with that is the user interface is going to let me override that value. So that's going to be this. And now we need to connect the two. Go connection from the stimulus for the light to the light neurons. And now we get this nice little connection that goes from here to here. Right. Cool. Let me zoom out a little bit. Now, if I right-click on the stimulus and I say slider, now I get a slider that lets me go ahead and control this input to this group of neurons. Go ahead and press play, and now I can go ahead and vary this input, and my neural activity changes. Maybe make this a little bit bigger. It's a little bit bigger. Yay, it goes and adjusts things. Nice. Yep. Cool. So nothing particularly fancy has happened yet. Right? The only thing that's happened here is leak, integrate, and fire neurons. We've got an input. It has randomly generated a set of connection weights such that these neurons have reasonable tuning curves. So that's the only interesting thing that's happened there. But other than that, it's just a pretty standard neuron model, some inputs. It's kind of nice that we've got this nice user interface for it. That's about the only thing that's fancy right now. We've got this varying input. One of the things that we sort of talked about in the video that I posted last is a lot of times, if you have a full neural network, it's not just an input in the hidden layer, there's also an output. Right? If I right-click on this thing and I say value, what it's going to do is it's going to say, well, all right, we want some output. We don't know, I haven't specified what output that we want. So by default, it's going to assume, it's going to make one that says, all right, I want an output that is whatever my input was. Right? So I want this to be computing the identity function. I want y equal to x. I want there to be, so there's some set of connection weights here that are taking the input and going into the group of neurons. And then there's some other set of connection weights that would take this activity up here and do a weighted sum of that activity to produce an output. Right? So it's just the second layer of a neural network. We can train that up however we want. The default in Nengo is just, all right, we randomly generate the input set of weights, and then we just use regression to solve for the second set of weights. So if I do that, now I get this. Okay. Pause that, go back in time a little. The interface lets me go back in time a little bit. So all that's happening here, so this plot here, it's the same data as this plot. We're just doing a weighted sum of these neurons. All right, we're doing a weighted sum of the neural activity. There's actually 100 neurons. We're only plotting 10 of them here. And the weighted sum of that activity, it's used regression to solve for, to find the set of weights that do a good job of making this little neural network be just the identity function. And that's what we get. We can go ahead and see, how accurate that is. We can go ahead and play with our inputs and sort of say, oh, hey, look, I'm putting in 0.14 and I'm getting out, yeah, about 0.14, somewhere nearby. Change the number of neurons, it'll be more accurate, things like that. A couple interesting caveats to pay attention for. So I've got this sort of range of inputs. What happens if I put in a larger value that's outside of this range? So I right-click on this and I say set range. I say -2 to 2. I haven't changed it, so like something is going to happen if I put in values outside of that range. So what's it going to do? Well, oh, okay. Well, the graph went off the top of the chart. That makes it harder to read. So I'm going to right-click on this graph and say set range -2 to 2. You can see the neural activity up there. No, it's still doing something. But you'll notice I'm putting in a 2 and it's outputting a 1.2. Why is it doing that? When I said that it used regression to solve for a set of connection weights, it had to choose some range of values to optimize over. Right? So what it was doing was it said, okay, I want to do the identity function. So it just sort of generated a bunch of random inputs and said the output should be the same as the input for each of those, but it needed to decide some range of values to do that optimization over. And the default range of values is -1 to 1. So that's one big reason. Another big reason that it's having problems outside of -1 to 1 is that the neuron tuning curves are also, when it generated these encoders, it needed to generate encoders that would give reasonable neural activity for these neurons, but it had to make an assumption about what range of inputs were going on in order for that to happen. If I start going outside of that range, now my neurons are just firing as fast as they possibly can. and we're, there's not much difference going on in here. So that means our neurons are starting to be pretty badly behaved, and it's, again, not going to be good at doing this task. Both of those two things are the reasons why whenever we're building one of these little networks and it's sort of doing some sort of, okay, make this network approximate this function, it's always approximating this function across some range of inputs. The other way to think of it is, and what's actually happening behind the scenes is we give it a function, it has to sample that function, it makes a bunch of random inputs to that function, and then calls the function in order to figure out what the outputs are for each of those inputs. That's just a big set of training data, right? That's just a big set of, for these inputs, here's the outputs. That's the same thing we did with all the neural networks. So it's doing that behind the scenes, but it needs to know what the range of values are that it's supposed to do that training over. Okay, you can adjust that range. It's one of the parameters on the ensemble. I can go ahead and say the radius is 2. Whoops, radius spelled correctly. I press play, and now it does a perfectly good job between -2 and 2. Okay. All right, so that's just a weird way of automatically training up networks and showing that, yes, it works fine with spiking neurons. That's really all we've shown so far. All right, so that's my group of neurons that's going to represent how bright the input is. We're also going to need to have an input that represents what direction the food is in. So let's make me one of those. Let's have some neurons. How many inputs does this network have? Now I think I'm going to go with 2. So that's going to give sort of how far away is the food in the x direction, how far away is the food in the y direction. It's a bunch of different possible ways we could represent that. This seems to be kind of nice in that it doesn't cause big discontinuities. Like we could have done like angle and distance, like do it in yeah, what's the angle and then how far away is it? But that would have caused problems in that you get this big discontinuity at pi and minus pi, or 180 degrees and minus 180 degrees. This style of representation at least avoids that discontinuity, so it simplifies things a little bit. But that's exactly the sort of decision that you make when trying to build these models. The nice thing is these sorts of decisions also end up having some sort of making biological claims, because we would have a different set of responses of the neurons depending on what decision you make. You can go ahead and look at the biology and find out which of these possible decisions is closest to what the biology is doing. This turns out to be a way that a lot of motor sort of XY sort of location seems to be representing in cortex. That's very consistent with there were some experiments by Georgopoulos in the motor cortex that this is very consistent with. Anyway, but exactly the same idea. We're also going to have some stimulus to let us go ahead and do that, or do that input. We're going to have be a default of 2 zeros, and we're going to go ahead and connect them. Function stim food to stim, whoops, to food. Cool. All right, it's starting to get messy. Let's go ahead and remove some of these graphs. We have our stim light, that, and our light. We have our food, and right click on this, I get a slider, and I get 2 sliders because I have 2 things to control. Okay, I go ahead and make a value plot, same plot as before. Let's actually pull up some spikes. Again, same as before. So now, again, I have 2 inputs going to this group of neurons. Here's some neural activity. If I go ahead and vary this input, that affects a bunch of them. If I go ahead and vary this one, that also affects a bunch of them. Importantly, it is just a layer of, it's just a set of connection weights there, and it's pretty close to all. So every one of these neurons is connected to both of these 2 sliders. Some of the connection weights might be close to 0 because they are randomly generated, but that is exactly the same thing as we've done before. And then this plot up here is, again, reading out of the features being in these, so these neurons are spiking, so they're producing this sort of activity, and then we're doing a weighted sum of this activity, and there's 2 different weighted sums for the 2 different outputs. So again, that's just those 2 weighted sums, that's just another way of saying the output connection weights. the connection weights from the hidden layer to an output. And we can go ahead and see, all right, it does a pretty good job of representing that. A couple weird things though. So one weird thing, so if I'm going to set this one to 0, I go ahead and vary this, that seems fine. It seems it's doing a perfectly good job. If I set this to 1, and I vary this one, why is the blue line changing? I'm only varying one of the inputs. Why is it doing a bad job? Now this wiggle that we're seeing up here, why is it doing a bad job of representing that? It's a little bit hard to visualize it this way, so I'm going to pull up a different plot to sort of see that. Same data, different plot. So this, I'm just going to plot it on a next. So instead of plotting this as 2 different lines, I'm going to plot it as a point in some space. Okay, so now as I move this around, okay, that all seems fine. So it's, again, it's the same data being plotted here as here. Just plotting it instead of over time, we're just plotting it as an XY plot. Excellent. If I go ahead and put it, so if I put the input there, that's what I was doing before, it's perfectly good at this. This is doing a good job. I go put this over here. Now we go up and down. Now this dot is not doing what I was expecting. Right? The ideal thing would be this dot would be going straight up and straight down, but it's not. And the reason it's not is exactly the same problem that we were showing up here when we started getting outside of the range. Okay, so this is just, I'm just driving home exactly the same point again. Again, when approximating a function, I haven't told it what function to approximate, so by default it's assuming I want the identity function. So I've got 2 values coming in, 2 values coming out. But when it found those connection weights, it needed to make an assumption about what range of values it's going to be optimized over. And the default in Nengo is, in higher dimensions now, it's this radius parameter, that's why we called it a radius, is it's a circle of some radius. So it's optimizing across that circle. The 0.11 is outside of that circle. It's not optimized for that point. It ends up representing something that's a little bit closer in. Okay? The same way when we put in values outside of the range up here, it ended up representing a value that's a little bit closer to the center. Cool. Okay, so it's just a side effect of the optimization. Again, we can go ahead and adjust that if we want by just adjusting the radius. This radius equals, and I guess the correct radius here would be square root of 2, which I'm going to call 1.4. And now it should do a much better job. Okay. Why don't I go ahead and just set the radius to 10 million so I don't have to worry about this? Well, if I go ahead and set the radius to, say, 10, it's much noisier now because it's optimizing across that entire space, and so it's going to be doing less good a job at this particular, at this particular region. All right, so that's always going to be the trade-off. I'm going to leave the radius back to 1 because that seems not too bad. I'm also going to put the light radius back to 1. And change this, set the range here, -1 to 1, and set our stimulus also range also to -1 to 1. Okay, so we have 2 tiny little networks that can just take in some input. Yay. And it is kind of nice that it's quick to train those. Just also to highlight it, like when I press this play button here, that's when it's doing that optimization. So you'll see a gear spin briefly. That is it doing that solving for all those connection weights. And these are simple little networks, so it's pretty fast for it to do that. All right. So we have something about the 2 sensor systems. Now, what is our action that we're supposed to be doing here? So if it's dark, go towards the food. If it's bright, go back to where you started from. So if this value is low, go towards the food. If it's high, go back to where you started from. Second one sounds complicated. Let's start with the first one. If it's dark, go towards the food. First thing I'm going to need is I'm going to need some group of neurons that represents my motor output. Fine. All right, we can do that. Motor is Nengo ensemble some number of neurons, whoops, neurons 200, dimensions 2, because I've got x and y. Now, if I wanted it to just go towards the food, right? If I wanted that to just be the action, then let's just do this. Connection, food to motor. What the heck did I just do there? So I just connected this group of neurons to this group of neurons. I didn't tell it anything about how to connect that. So what the heck did Nengo do? What Nengo did is it assumed that what I meant, I didn't specify anything, so it just assumed that I meant the identity function. So it assumed that what I meant was find connection weights between, there's 200 neurons here and 200 neurons here, such that whatever information is in here will get passed to here. So it's using the identity function to compute the decoder. It's got the randomly generated encoders here, and it's going to multiply those two things together to get the actual connection weights between the food and the motor. Exactly the same thing as we talked about in the last video. I'm going to show this. And now we go ahead and pass information from one group of neurons to the next. Now I do want to highlight that it's not like it's doing sort of a, oh, hey, look, that's an easy thing to do. I've got 200 neurons here and 200 neurons here. I just connect the first neuron in this one to the first neuron here, and the second neuron to the second neuron, the third neuron to the third neuron. It's not what's happening here, because there's nothing that's forcing us to have the same number of neurons. Like I could have 50 neurons over here. I can still do it. It's a little bit less accurate. Okay. So it's just find me the connection weights, because these neurons could have different properties. It could be a different type of neuron. These could be spiking neurons. These could be non-spiking neurons. It's just going to go ahead and find the connection weights for whatever function I want there. Okay. I don't know, up to 300 neurons. It'll be fine for that. All right. All we're doing, making a couple little neural networks, taking the output. So this is just exactly an example of what I showed at the beginning in the previous video of you just make two neural networks and you just connect the output from one to the input to the next. And then if you want to turn this into connection weights, you just do that trick of, okay, multiply the output connection weights from this network by the input connection weights from this network. And now I have something that will just pass, that will just approximate that function. This particular function is a really simple function, which is the identity function. I can do a more complicated function, though. So let's say I want a different function. Let's say my function. Oops, my function. I don't know. What function do I want? I want the function. So x is two-dimensional. So I'm going to say, I don't know, return the negative of x1 and x0. Okay, so that's some function. Okay. Now all I've done is I've told it when it makes this connection, make the connection weights to approximate this function. It's going to take that function, it's going to turn it into a bunch of training data by randomly generating a bunch of x values, calling this function to find out what the output is for each of those values, and then using that to train up the neural network. I will note that if instead of defining it as a function, if you just have a bunch of training data of just, okay, here's the inputs and outputs to use, you can also just specify that. But you can do it this way. And now when I go ahead and vary this, it's doing what I want. Right. Of course, there's nothing limiting us to simple functions. I could do more complicated functions. I could do, I don't know, x0 times x1, and I don't know, the sine of x1. I should import numpy if I want. Import numpy as np. There we are. Now I've got a more complicated function. Oh, yep, multiplying by 0 is 0. That's a good sign. Yep. Okay. All right, I'd have to do some fiddling around in order to figure out whether or not this is the function that I specified, but I think so. Right? So the only thing that's going to be different here is as I do a more complicated function, it's going to be harder for the neurons to approximate that, depending on the function. Okay. Sweet. All right. Oh, there's also nothing that forces me to make sure that it's the same number of dimensions. So if I just say I wanted, I don't know, let's say it just computes one thing. So it's just computing, here's 2 values, but now the return value is going to be one thing. Where it's going to cause a problem is we're going to get an error here that says, oh, hold on a second, there's a problem with this connection. Size 1 is not equal to size 2. Yeah, so it's saying that the function that's coming out of here has 1 value, but this motor thing that I'm supposed to connect it to has 2 values. I can't connect those up. So one thing I could do is I could just change motor to be one-dimensional. Oh, right, and then this plot doesn't mean anything, so let's make this plot. Pretty hard to do an XY plot when you've only got one thing. Okay, so now it's doing that. Alternatively, if I want to leave it as 2 dimensions, what I could have done is I could have said something like that. Right? And that would be saying, all right, take the output from the food, or compute this function, but now this function has a 0 in it, so it's not going to affect, so it's still going to be 2 values, but it's just not going to be interesting in one of the dimensions. So it's only affecting the first dimension that's being represented there. We could also, of course, have done this. Right, now it'll affect the other dimension. Right. Because this sort of thing ends up being kind of useful, we actually also have a shortcut in Nengo for doing it. I can just define this, and then I can say motor 0. Okay. And what that's going to say is send that into the first dimension of the motor population. This supports the Python slicing notation, so you can even, you can do fancier things like go into the last dimension or go into the first 2 dimensions, or however, those sorts of notations also work. Of course, all of that is overkill for what we're doing right now. So I'm just going to delete all of that and say, all right, I have something that will just pass the data from the food to the motor system. But that's not what we want. I want this if it's dark thing happening. So if I was a programmer, one way I could think about what's going on, if I wasn't constrained to just do everything by neurons, then really what I want is I want this group of neurons here to affect this connection. All right, so like only make this connection happen if the light is, if these neurons are representing a small value. But biology can't just make connections appear and disappear like that. So I need to do something else instead. And in fact, I've introduced all of the tools needed to do that. It's just a little surprising what we're going to do here. One way we can think about it now is, hold on a second, the function that I really want to implement, if I wanted to treat this as a function, this is a function that has 3 variables as an input and 2 as an output. The 3 variables are how bright is it and where is the food, and then the output is some motor thing. So let's rephrase this as I want to make this as a group of neurons that has 3 dimensions, and I'm going to implement that as an output that's coming out here. Okay, don't know if that made any sense. Let's build it. So we're going to call this population, I don't know whether or not to do food, I guess. Ensemble neurons is, it's getting bigger. We'll go up to 300 neurons. Put this back down to 200. I generally do a rule of thumb of somewhere around 100 neurons per dimension, just to sort of keep a reasonable amount of accuracy, or a similar amount of accuracy. If your computer is bigger, use a bigger number, or if you are I tend to do overkill for the number of neurons, and then if I'm comparing to a particular biological system, I might slowly reduce the number of neurons. But the dimensions is 3. I'm going to make a connection from the light into this do food. I can't just do that because the light is 1 value and do food is 3 values. So I'm going to use that trick that I just specified and says, hey, put that into the first dimension. Python's a programming language that starts counting at 0, so square bracket 0 is the first dimension. And I'm going to make a connection from the food to do food, and that will be the other 2 dimensions. Okay. So again, all I'm doing now is finding connection weights such that this group of neurons now has the information, this value and these 2 values. Now I can make a set of connections coming out of this. Okay. So my food, this is going to be a function to define. This x has 3 values in it, and I'm going to get confused if I just refer to them as x0, x1, and x2, so I'm just going to give them reasonable names. So this is light, food x, and food y. That's the 3 values. Now I can say, all right, if it's dark, go towards the food. If light is less than 0, food x, food y, otherwise return 0. Okay, so that's a function that is this action. It's dark. If it's dark, go towards the food. If I go ahead and say, make a connection from do food to motor, where the function is that food func. Oh, and I suppose, one nice thing about having this diagram is this reminded me that, oh, I left in this bottom connection. Let's get rid of that one. Okay. It's going to go ahead and find set of connections. So it's going to take this function, it's going to sample, it's going to turn it into a bunch of training data, it's going to train up this network, it's going to go ahead and connect everything up. And we'll just go ahead and try that, and then we'll fix it, because there's one small tweak that we'll want to make to it. All right, so let's make it dark. Good. The food is nowhere, motor's nowhere, fine. Now I'm just going to say, okay, cool, good. Now I can go move around. Good, so it's now chasing after wherever I put the food, it goes in that direction. That's fine. If I make it bright out, now it doesn't go chase after the food. That's kind of nice, right? One small tweak that I should have done is this do food function got optimized, which has the default radius of 1. In this situation where I have food over here and food and light up there, I'm feeding in. Actually, we can go ahead and take a look at the values being represented in here. Let's go ahead and look at those values. Right, I'm going to feed in some light, feed in some food, and you'll notice that it's not quite representing 1 and 1. Right? And also you're getting the side effect of, oh, look, there's a little bit, it's not quite at 0 here. Right? Why is that? Again, the radius problem. I'm now feeding in a value that is well outside the range of the actual radius, so I'm going to increase the radius a bit. As long as I know what range of values I'm likely to put in, that should be fine. Okay, so now we should be doing a better job of doing that, and we should be doing a better job. We're still doing a little bit off of exactly that 0, but that should be in general better. Okay. Cool. All right, so we've now built a really weird neural network that goes ahead and implements that sort of first action. Now we want to do this other part. This looks harder. Go back to where you started from. In order to get that, I need to know where I am. How the heck am I going to keep track of where I am? Well, I know my motor behavior. I mean, in a real complicated system, we would have some sort of sensory information. You can observe the world moving around you, and there's a whole research area about how to do that sort of stuff. For the case here, well, hold on a second. We know our motor action. If we just sort of initialize our starting position at 0, and then we just change that value based on this motor action, we should be able to keep track of where we are. And that is the definition of an integrator. So what do we, if this motor thing, if this is sort of like the velocity that we're moving at, then our position is the integral of velocity. Cool. So let's do that, because we had this whole section on how to compute the integral. So, fine. Our position is a Nengo ensemble with some number of neurons. We'll give it a little bit more. It's two dimensions, because it's representing a position. And I gave a whole bunch of weird math in order to implement any arbitrary differential equation. The integral is a nice special case. And you can work through exactly why if you go back and look at the math in the previous video. But this is a nice, easy one to just always remember. And that all I have to do is I make a connection from those neurons back to themselves. And the how stable that integrator is does depend on exactly on what synapse model we're using. So I'm going to make things life is a little bit harder or easier for the system, and I'm going to use a fairly long time constant. So that's a 100 millisecond time constant on our synapse. I guess I didn't specify that. Every single time you make a connection in Nengo, you can specify a synapse. Just the same way as those diagrams that I was showing before in the previous video. The default synapse is a 5 millisecond one. So it's a fairly fast synapse. So it always puts in one of those anyway. You can set it to 0 if you want. So that's something you can always specify. If you just specify a number, then you get an exponential decaying synapse. You can also specify a full synapse model and do alpha synapses and other more complicated synapse models. But that's sort of the default. So I'm going to use a connection which has a fairly long time constant back to itself. But the function that I'm computing there, because I haven't specified, so it defaults the identity function. And that kind of makes sense in that if 0 is being fed into this thing, this is our group of neurons for the input, if 0 is being fed in, then the recurrent connection should just send whatever value I'm currently representing, send it back to itself. So it kind of makes, that's what the math ends up saying, and it kind of makes some intuitive sense there. In order to do an input to this integrator, though, we make a connection from the motor to the position. And the function that the math, and we should specify the same synapse. The math says the function you should compute on this function is the identity function, or y should be x times whatever your time constant is, x times 0.1 in this case. I could specify that as a function. Again, since that's this sort of like multiplying by a constant is a really simple function, instead of doing the syntax to specify a function, I'm just going to say, here's another shortcut that you can do in Nengo, which is just say transform equals 0.1. So that's sort of an implicitly saying a function that takes the input and multiplies by 0.1. Okay, so just a shortcut for that. Let's shrink that text a little bit. There we are. All right. Fine. I now have a group of neurons that in theory should represent the integral of motor. Does that work? All right. I'm going to make it dark. I'm going to say go to the right. Ooh, and it goes to the right. I say go to the left. It goes to the left. I say don't move. It stays there. Go up. It goes up. Okay. And I want to just sort of highlight what's happening there because it's kind of, if we actually just look at, say, the firing pattern of these neurons, nothing, again, it's all just neurons when we're running the simulation. It's just a bunch of neurons with this big recurrent connection that got defined in a really weird way, right? All we're doing is changing some inputs going to some of these neurons, and we're getting some neural activity. You can see it changing as we go to different points in the space, but it's found something where if I feed in 0, now it's not perfect. It does drift a little bit, as you can see, and you can do fun experiments like measuring how much of a drift you get. You go up with more neurons. There we go, I have 5,000 neurons now. Oops, come on. It's going to take a little longer to think, because it's got to optimize all 5,000 neurons, right? But now we should have, things should be a little bit more stable. Oops, make it bright, dark out. Go that way, go this way. Right? So these neurons are now keeping track of position. So we now have a memory inside our neuron model. I will warn you, 5,000 neurons starts... the total number of neurons in the model is not all that expensive, is fine for running simulations, but when it's doing the optimization, the number of neurons in a single ensemble can make it difficult to, if that number goes too big, it can take a long time to do that optimization. So 5,000 was probably pushing it, depending on what hardware you have. Again, this is where you start needing more computers, and it's just different ways. There's ways of doing that regression in different ways, but the default way of doing that regression to find those output decoder weights, avoid really big numbers. Any case, right, so we now have a group of neurons that can represent the position that I'm at. So now I'm in good shape to go and implement this other action. If it's bright, go back to where you started from. How am I going to do that? Same trick as before. Let's go ahead and remove that. Starting to... yeah, we'll leave that there. We are going to make a do home ensemble. Ensemble, 300, dimensions is 3, radius is 1.5. Sure, we'll do that. Do the same tricks of make a connection from the light to do home, the first element, make a connection from, now it's going to be from position to the do home those elements. So that all that data is going to go into here. Now the function that I want to create, I'm just going to copy that and paste it. So that's going to be my home function. And this is going to be my position x, position y. If the light is greater than 0, so if it's bright out, I'm supposed to return to where I started from. So that's go in the negative of the position direction and the negative of the food direction, or whoops, the negative of the position direction for y. Otherwise do nothing. And now I want a connection from do home to motor that does the home function. Okay. What the heck is that going to do? All right, let's make it dark. Food is, we're not moving, we're not going in any direction, our position isn't changing. I'm going to say, hey, look, there's food to the right, and off it goes to the right. And then I'm going to say, all right, it's bright out. And it runs back to where it started from. And in fact, it's sort of ignoring, go over there, there's food over there, there's food over there. No, it's totally ignoring the food because it's too bright out, it's scared, it's going to stay home. And then I make it dark again, and off it goes. Okay, so this sort of is moving around, it's in the dark, it's nice and safe, I can go scare it, and it heads back home. Cool. So that is a really weird way of building neural networks. A couple sort of take-home messages out of that. One is you tend to end up with these sorts of diagrams where like, stuff is connected all over the place and there's big giant loops and things. I think that's a good sign because, hey, that does tend to be how biology tends to look. There's also a bunch of processes we could do to sort of optimize and modify these sorts of things. If we wanted to do a better job of comparing the components to biology, we could do all sorts of things like, well, how accurate are you with a certain number of neurons, or what does the firing activity at different points, how well does that map onto the biology? Those sorts of things are all possible. Taking a look at the actual connection weights. Because again, all of this stuff that I'm doing here is just a weird way of specifying connection weights. At the end of the day, it is just a bunch of leaky, integrate, and fire neurons that are connected together, or whatever other neuron model you feel like. You can do all this with sigmoid neurons, or rectified linear, or Zakovich neurons, or whatever other sort of neuron model I feel like I can use this process. It'll be a different set of connection weights because they're different neurons, but I don't have to change this code much because it sort of encapsulates all of that. And the only thing I have to do is specify, change what neuron model to use. Cool. So I hope that gives a little bit of feel for the weird process that we go through for implementing brains this way. It's sort of like normal programming. It's not quite exactly the same. There's all sorts of weird caveats. So, for example, this if statement, this less than 0 greater than 0. I didn't really play around with, well, what happens when the light is near 0? Right? It still runs after food. A little bit. Actually, it ends up running sort of less quickly as it's near the food. Right? And that's a side effect of it approximating. I've asked it to approximate a really, really sharp function, a function that changes really quickly right at one point. It's going to end up finding a sort of a smooth version of this function. So it's not going to do, exactly, like the difference between an input of minus 0.1 here and plus 0.01, if I give it, look, let's make it a little bit dark. All right. Yeah, it sort of explores a little bit. Make it, if I make it a little bit light, all right, it's going to head back to home a little bit. Doesn't quite make it home. It's like, all right, that's fine. I'm okay here. There's food up that way. So, it's not perfectly choosing between these two actions. So it's sort of a little bit following the food and sort of a little bit running home. And that's something that there's nothing in this algorithm, as I've specified, to say that. It's just a side effect of approximating this algorithm. Sometimes that's what you want, sometimes it's not what you want. But that's sort of going to be a side effect of this sort of style of implementation. And sort of expanding that, the effort of how do you scale this up in terms of, well, what if you have many actions? That actually led to a lot of research that I did on something where as you expand that up and you start building systems to start doing this better and better with more and more actions, you end up with something that looks a lot like the basal ganglia. So that's kind of cool. It's a whole side line of research of my own. Yeah, you get this interesting interaction between both the behavior of the model and the low-level neural assumptions that you're making. And I really like that because it lets you try out different neural assumptions, go see what the behavior is like, and those actually become testable predictions and things like that. Anyway, I hope that has given you a little bit of an intro to how you build things in this really weird sort of way and try to build up complicated systems where the only components you have are neural networks. Yeah, and so that's the neural engineering framework. Thank you very much, and we will see you next time. Bye.